Hi, my name is Júlio. I'm a postdoc in the Institute of Pure and Applied Mathematics in Brazil. I would like to start this talk by asking if the following problem has ever happened to you. Suppose you are in an application where you're training learning models using samples from a source geospatial domain. You perform cross-validation to estimate the generalization error of all these models. You then select the best model to make predictions on a target geospatial domain. When the results come, you are informed that the model performance is quite poor and that the actual error of the model is prohibitively high for the application. Why this happened? There are many reasons why this may happen. One of them is the fact that geospatial processes have spatial correlation. For example, if you have two Gaussian processes Z1 and Z2 and their corresponding feature space drawn at the bottom, as we increase the spatial correlation length from 0 pixels to 80 pixels, this feature space gets deformed. If the deformation in the source geospatial domain is different from the deformation in the target geospatial domain, the performance of your learning model will be degraded considerably. Another reason is covariate shift. If you train a model in a given geospatial domain and try to apply this model in a different domain, it may be the case that the covariate distribution in the source is very different from the distribution in the target, also compromising the performance of the model and all methodologies such as cross-validation. Here we will compare three estimators of generalization error: classical cross-validation, block cross-validation, and density ratio validation. All these estimators belong to the same family of estimators based on this splitting strategy, where the source domain is split into k folds, in the illustration k equals to 4 folds, and the estimate of the error of the model H is an average of this error inside of each of these folds. These three methods differ in the way they partition the source domain and in the way they weigh the samples inside each of these folds. In classical cross-validation, the folds are generated at random. I'm illustrating these folds with colors. I have a fold in red, yellow, green, and orange color. And by hiding one of the folds and training the model in the other folds, we can then estimate the error using the predictions in the fold that was hidden. The problem with cross-validation, as shown here, is that samples that are nearby in physical space have very similar feature, and so this estimate of error is super optimistic. Using that fact, the literature proposed different methods, such as block cross-validation and leave ball out, where the partition is not random anymore, but it's systematic. You create folds with a given size, for example, a size that's equal to the correlation length of this spatial process, and then you move this box over this domain to estimate the error. For each fold that's hidden in red color, you create a dead zone where you cannot use samples, and then you train the model with the samples that are outside this dead zone. Similarly, in leave ball out, we hide the center of a ball of radius r and train the model with the remaining samples outside the ball. The third method we will compare comes from the transfer learning literature. Density ratio validation is a variant of importance-weighted cross-validation. In this case, all the examples in the source domain are assigned weights, which are density ratios between the probability density of covariates in the target and the probability density of covariates in the source. These density ratios are approximated with basis functions. And via kernel methods, we can minimize the square difference to obtain an approximation. So in summary, we have three methods that will be compared in the following experiments. We have two experiments to share. In the first experiment, we have full control of the distribution. We have Gaussian process data. In the second experiment, we have real data from the New Zealand Public Data Pack. In the first experiment, we consider two Gaussian processes, Z1 and Z2, on a grid. We denote their constant mean and variogram mu and gamma. In this case, by stacking these two variables, we get a feature vector, which is bivariate Gaussian, with some given mean and variance. If we fix these two Gaussian processes on the source domain and vary the parameters of the two Gaussian processes on the target domain, we introduce covariate shift. The circle in grayish color represents the source domain, and the circle in reddish color represents the target domain. By varying these parameters, we can find ourselves in three different configurations. When the target domain is fully inside the source domain, we have the configuration called inside. When there is partial overlap, we have the partial configuration. And when we are completely outside the source domain where the model was trained, we are in the outside configuration. We can define this covariate shift in terms of two parameters, a shift in the mean and a shift in the variance. We also play with the spatial correlation, which in this experiment can be 0, 10, or 20 pixels in the grid. These three configurations can be expressed analytically with these three expressions. For each covariate delta tau in this unit box, we define the novelty factor, or the difficulty of the problem, as being what's outside of the source domain A minus what's inside in the intersection, normalized by the size of this target domain. This novelty factor can be normalized to be a measure in between 0 and 1. For each feature vector, which is the vector of the variable Z1 and Z2, we can assign a known label in this completely made out experiment, where the feature vector is assigned this alternating pattern with a norm function. The experiment is therefore the following. For each shift and each spatial correlation, we pick a learning model H and perform the following steps. We sample a learning problem with that covariate shift and spatial correlation using Gaussian simulation, the LU decomposition method. We estimate the generalization error of the model with the three estimators, classical, block, and density ratio validation. And then we estimate the actual error with Monte Carlo simulation, given that we can generate hundreds of Gaussian simulations with geostatistical simulation. We then plot the error of these problems, of this model in the problems versus the novelty factor. As we can see here in the bottom, in the upper part of the plot, we have the error of these three methods as a function of the novelty factor, which is a measure of how difficult the problem is. From a very simple problem to a very difficult problem with novelty 1. The colors of the dots represent the correlation length, where 0 correlation is the green, 10 pixels of correlation is purple, and 20 pixels of correlation is orange. The first thing we observe is that both classical cross-validation and block cross-validation are insensitive to covariate shift as expected. These methods were not developed to take into account shifts between the source and the target domain. We also observed that the block cross-validation estimates increase as we increase the block size or the correlation length. And this indicates bias because of the systematic partition of the folds. Although the density ratio validation estimation method tries to follow the increase of error of the model, it's not exactly equal to the rate of increase obtained with Monte Carlo simulation. Here we present the results in a different way. We group each of the methods with a different color and fit a smooth fit to these points to observe the patterns more clearly. So for zero correlation, zero spatial correlation, 10 pixels of correlation and 20 pixels of correlation, we observe that none of these three methods can actually match the actual error obtained with Monte Carlo simulation. There's always a gap between the error of the model, the actual error, and the error that was estimated with the three methods. We also use the QQ plot for the inside configuration where these three methods are reasonable to compare to show that the block cross-validation is indeed biased with the systematic partition and that the classical cross-validation gets super optimistic. In the second experiment, we get 400 well logs from the Taranaki Basin in New Zealand. In this case, the learning problem is the following. We define our source domain as onshore wells, and we have the following covariates to train the model. 5 logs, gamma ray, potential, DTC, density, and neutron porosity. Training the model in onshore wells and trying to make predictions in offshore wells, we see that these covariates shift. Our goal is to predict the rock formation, which is a classification problem with 2 possible classes, Uranui and Manganui types of formation. If you train a collection of models on this problem, we can then rank these models according to their generalization error. Here is the list of models we have tried, where the dummy model is just a model that reproduces the marginal distribution of labels. We have a column of error of the model in the source domain, the onshore wells, and this column of target error is just shown here for reference. It's not available when the model is trained. These are the offshore wells. The first thing we notice is that the cross-validation method estimates error that are super optimistic. And so this red color indicates that these numbers are far away from the target column. And the blue color indicates the methods that get estimates of error that are closer to the target error. We see that the block cross-validation estimates are conservative. They're always higher than the cross-validation because of the blocking mechanism. But all these 3 methods, they fail to rank the models according to the actual error they had in the offshore wells. So if you use this column of target errors in the offshore wells to rank the models, you get this optimal ranking, where the model that best performs in offshore is linear discriminant analysis. However, all 3 methods rank the models that are more complex at the top incorrectly and put the models that are simple, like linear models, at the bottom, where these linear models have better generalization. If we repeat the experiment by mixing up onshore and offshore wells, that is, we remove the covariate shift, we start to see that cross-validation starts to get good estimates of the actual error, and that the block cross-validation method, as a conservative method, becomes too pessimistic. In this case, all the models are successfully ranked by 3 of the estimators. As our conclusions, we can see that the blocking mechanism only guarantees that the block cross-validation estimates are higher than the CV estimates. When there is no covariate shift, the block cross-validation estimates are necessarily pessimistic. The cross-validation estimator is not adequate for problems that show forms of covariate shift. These situations are rare in geospatial settings, and the density ratio estimator performs reasonably well in both situations and is recommended instead. Both cross-validation and density ratio estimators, they suffer from a serious issue, which is the issue of dealing with overfitted models, in which case they largely underestimate the generalization error. In risk-averse applications, the block cross-validation estimator is recommended instead. The general message here is that none of the 3 estimators is capable of ranking learning models correctly under covariate shift and spatial correlation. And we argue that we need a new learning framework to reason about these problems and develop new estimators. You can find more information in our paper, Geostatistical Learning Challenges and Opportunities, recently published in Frontiers in Applied Mathematics and Statistics. We welcome you to join this effort in this open source project, Geostats2021. Thank you.